The work that I'm going to be presenting today has been jointly done by myself, as well as my supervisors, Michael Wallace and Grace Yee. So if I'm successful with my talk today, then by the end of it, I should have briefly introduced what measurement error is, demonstrated the impacts of ignoring measurement error, even in simple models, and show how an analyst may use a technique known as simulation extrapolation to correct for these impacts of measurement error. Then, motivated by a desire to accommodate non-normal errors, I'll briefly introduce our non-parametric extension to the simulation extrapolation methodology, which resolves some of these concerns. In order to motivate these discussions, I want to consider a fairly simple statistical modeling setup. So suppose that we wish to assess what the impact of BMI is on the likelihood that an individual has hypertension. This example is motivated by an analysis of the Korean longitudinal study of aging, which is a study of individuals aged 45 and older in Korea, and it seeks to investigate patterns related to the determinants of health throughout aging. While this analysis is on the surface very straightforward, the BMI that's recorded in the study is the result from individuals self-reporting their weight and their height, at least for most respondents. We know, both from past research and from a subsample of the data where clinical measurements were taken, that the self-reported values for the weight and height are error-prone. So that is, we can view an individual's self-reported BMI as some combination of their true BMI plus an amount of random noise that's perturbing this value. This is a setting that we're going to commonly call measurement error, or more specifically additive measurement error, and even in simple settings it creates some major issues with estimation. So to introduce why we care about measurement error, let's take a moment to make our goals slightly more concrete. The data that I'm going to be presenting today are simulated so that we can see the impact of different assumptions, but they are based around the Korean longitudinal study of aging. So in our data set for each individual, we make observations of an outcome variable y, which is a binary indicator of whether the individual is hypertensive or not, an age variable, which will denote w, and we assume that this is going to be measured without any appreciable error, an error-prone version of the BMI, which will denote x star, and this is error-prone owing to the fact that it's self-reported. We assume that x star is going to equal the true value x plus some noise term. Then for a subset of the individuals, we also observe x, which is the true BMI as has been measured in a clinical setting, and we'll be able to use this subset to make judgments regarding the degree and the distribution of the error terms. Our goal in this setting is then straightforward. We want to estimate the probability that an individual is hypertensive given their age and their true BMI, using just the data that we have on hand. So here we have some box plots from a small simulation in this setting, and these box plots here are for the slope coefficients for the BMI variable in a standard logistic regression. If we assume that the true values for each individual are available, then the simulated results consistently estimate the true regression coefficient. However, if we naively use the reported BMI in place of the true BMI, we see that the results become very evidently biased. So that's the lower box far away from the dotted line. The sign on the coefficients of this analysis remains the same, but the magnitude is going to be roughly halved. And in other situations where we have this same additive measurement error setup, it's going to be even harder or less predictable to know what's going to happen if we ignore the impacts of the measurement error. So we can see the sign might flip on regression coefficients, we can see the magnitude might be amplified. And so because of this, this motivates the need to come up with methods of correcting for these effects. Now, in particular, we care deeply about coming up with corrections for these when we want to know what's the true relationship between, say, BMI and hypertension, right? When we care about what is the true underlying relationship, then it's important that we find ways of remedying these estimators. So while many correction techniques do exist, the core one which we'll focus on today is known as simulation extrapolation, or SIMEX. The basic underlying process of simulation extrapolation is summarized through a two-step procedure. In the first step, we take our variables of interest, we add extra error to it, and then using the variable with additional error, we compute the estimators of interest. We do this with progressively more and more error, and each time we'll fit this estimator of interest. Once we have several different versions of this estimator fit to the data that had extra error, we fit a model to these data. And this model characterizes what's the relationship between adding extra error and our estimator of interest. With this model on hand, we can then extrapolate backwards to determine what would happen if instead of adding extra error, we removed error. So this is known as the extrapolation step. It's worth pausing for a moment to try to develop an intuition of why this works. The model that we are working with is this additive error model, where we have assumed that x star is the true x plus an error term, which we're calling u. Now, suppose, as is common to assume, that the error terms follow a normal distribution, and in particular, we're going to take this to be normally distributed with mean 0 and a variance, say, sigma u squared. The first step of SIMEX has us adding extra error to this term. So let's say that the amount of extra error we add is mediated by a parameter, call it lambda. By the amount of error, we're thinking primarily about the variance of the error terms. So let's say that independently of everything else, we add some extra error, which follows a normal distribution with mean 0 and variance given by lambda times by the variance of u. We can think about this quantity as being another error-prone realization of the truth, and we're going to compute the estimator using this proxy variable here. Importantly, since both u and this new error term are normally distributed, and since they're independent by assumption, when added together, the errors for x star of lambda is going to follow a normal distribution with mean 0 and variance given by 1 plus lambda times the variance of u. Now, if the errors here are independent of the true x, then we can start to see the premise of why SIMEX works as an error correction technique. Conditional on the true x, this error-prone version will have an expectation given by x, and it will have variance given by 1 plus lambda times the variance of u. We can only generate values of realizations of this for values of lambda which are at least 0, since we have to take the square root of lambda. However, conceptually, if we were able to set lambda to be equal to -1, then the variance of this quantity would tend towards 0. As a result, the intuition here is that the variance of this remeasured quantity, x star of lambda, goes to 0, and it remains centered on x, as lambda tends towards -1. Correspondingly, the estimator, supposing it's sufficiently smooth, should also tend to the estimator had the truth been observed. We can see this in action here. So this is the result from a single iteration of a logistic regression, and note in this case that the true value for the coefficient is set to be 1. We begin by fitting the model to the data that we observe, which in our notation from above represents taking lambda equal 0. Next, we add some additional error and then refit the model of interest here. This corresponds to taking lambda to be slightly more than 0. We can continue doing this, add some error, fit the model, for increasing values of lambda on some predefined grid. Once we have these observations, what we do is fit a parametric model that predicts the estimated theta based on lambda. Now, this is a standard model fitting procedure, and while there are commonly chosen models, any technique that you desire could be used here. Once you have this model, you simply extrapolate back to lambda equals -1. This estimated value at -1 is taken to be a corrected version of this estimate. If the model is correctly specified and some regularity conditions are met, then this will be a consistent estimator of the truth, as we can see in this case. In practice, oftentimes the true model will not be known, and so often this procedure is applied as a method of reducing the bias, producing approximately consistent results rather than exactly consistent results. But a big benefit to this procedure is that it's estimator agnostic, and it also can be implemented using entirely conventional software for basically any analysis that you're doing. So to the previous simulation, we now add the results from a SIMEX correction. I would note here that I'm presenting results that are more common for a true analysis. I used a fairly standard model for the extrapolation step rather than working with the exactly correct extrapolant. We can see that compared to the naive analysis, the SIMEX procedure produces far more reliable estimators. There are techniques to make this perform even better, but even as a first pass, we can see that this is much improved. Now, the big problem with this analysis as presented is that we have assumed that the errors are normally distributed. In some settings, this is a reasonable assumption. Often, however, the observed errors are going to be highly non-normal. We often observe skewed errors or heavy-tailed errors, and in these cases, the underlying assumptions of SIMEX fall down. With the mathematical intuition we discussed earlier, we can understand why this is the case by considering that if U is not normally distributed, then the pseudo-errors that we add on are not going to simplify down in the way that we saw. These results show the reintroduction of bias when we use non-normal errors. So the SIMEX correction still improves over the naive estimator here, but it's substantially worse than when the errors are normally distributed. The degree to which violations of these assumptions matter in practice is going to depend heavily on the underlying models, but these assumptions results should at least give us some pause. Now, fortunately, we can relax this assumption. So we propose a non-parametric SIMEX procedure, denoted NP-SIMEX, which does not make any distributional assumptions on the errors. Functionally, the procedure is exactly the same. We simulate additional error, fit a model to the resulting estimates, and then extrapolate these results back to the case where lambda equals -1. However, the key difference in the method is that our errors do not come from a normal distribution, but instead from the empirical error distribution. So for a grid of integer valued lambda, we sample lambda realizations for every individual from the empirical distribution. These errors are added on in exactly the same way as before to form x star of lambda. Now, we demonstrate that as lambda goes to -1, this procedure has all of the same properties as the standard parametric simulation extrapolation under certain formal regularity conditions. Our procedure can be thought of as analogous to the non-parametric bootstrap, where sampling occurs based on an empirical distribution rather than on some imposed distribution. Now, our method is designed to be able to slot into the toolkit of an analyst who's already using simulation extrapolation as easily as is possible. If you're interested, I have an implementation in R that's still in development, but which is available on my GitHub. The link's on the slide, but you're also more than welcome to reach out to me and I can point you towards it. So, armed with this, we can turn back to the simulation results and see how it fares. And we see that the NP-SIMEX method appears to make further improvements to the SIMEX procedure, returning to the results that are far closer to what we saw when we assumed normality with the standard SIMEX. It's worth commenting on the variance of these estimators, which are quite clearly larger than the other techniques. Now, this is in part due to the fact that this is a non-parametric procedure. It's also in part due to the specific simulation that we're considering here. So to give a quick wrap up of the main contributions here, the NP-SIMEX is capable of correcting for errors and variables under any distributional assumptions, assuming that you have validation sample. If, as is common in measurement error literature, a validation sample is not available, we can use the NP-SIMEX assuming that we have replicated measurements. In this case, we do need to make some distributional assumptions, but they can be fairly broad. So for instance, we show that the NP-SIMEX procedure can be implemented using replicate data if we assume that the errors follow any symmetric distribution. We also extend the NP-SIMEX technique to the situation where errors are dependent on the true values, which, as you may imagine, will commonly be the case. This relies on some kernel density techniques, but is otherwise a very similar procedure. And then under regularity conditions, the estimators are consistent, asymptotically normal, and behave in a very similar way to other non-parametric estimators that you might be more familiar with. So as a brief summary, we've shown that by resampling from the empirical error distribution, this provides a way of rendering the SIMEX estimators valid for any distribution while maintaining the same basic underlying procedure. So I will leave my discussion there for now. Thank you all for listening. And if you have any questions, I would be more than happy to answer them. You can feel free to reach out to me directly.